The last aspect here refers specific to the renal circulation. Now, the renal circulation is characterized by having a venous PO2 that's extremely high compared to other systemic tissues. The venous PO2 in the renal circuit is high because it is basically an overperfused circuit. The renal circuit gets more blood than is required to supply oxygen and nutrients to the tissue. The high blood flow through the renal circuit is to supply fluid to filter. The bottom line point is, if a tissue is overperfused in the systemic circuit, it will have a high venous PO2. If a circuit in the systemic circuit is underperfused, it would have a low venous PO2. If a circulation in the systemic circuit is overperfused, then it is getting more blood than it requires for tissue metabolism, and the venous P will be high. If a circuit is underperfused, then it is not getting as much blood as is required, and therefore the venous PO2 will be down. Now, just extending that information, if you give an alpha blocker then to the systemic circuit, it will tend to dilate the arterioles, and therefore the tissue will be overperfused, and as a result, the venous PO2 should increase. On the other hand, if you give an alpha agonist, that will cause the arterioles to constrict, therefore you decrease the flow, you would now tend to underperfuse the tissue, and therefore the venous PO2 would go down. And I know those relationships are tested on step 1 then, so they're important to remember. Now that finishes off the characteristics of the systemic circuit that we have to deal with. I now want to switch to the pulmonary circuit. And you should realize the pulmonary circuit has completely different characteristics from the systemic circuit. They quite often have a single question to test your understanding of the characteristics of the pulmonary circuit. This is usually a poorly answered question because people just do not spend the time to understand the basic characteristics in the pulmonary circuit. Now, we've listed these on the slide here, and these are the important characteristics of the pulmonary circuit. First of all, the pulmonary circuit is a low pressure circuit. Compared to the systemic circuit, then, these pressures are fairly low. The next point is the pulmonary circuit is considered a high flow circuit. It receives the entire cardiac output, then 100% of cardiac output flows to the pulmonary circuit. Now, as we said previously, if you combine the first two characteristics here, that is, you have a low pressure circuit with very high flow, that must mean it's a very low resistance circuit. So the pulmonary circuit, because it is a low pressure, high flow circuit, it must be a very low resistance circuit. Now, another important characteristic is the pulmonary circuit is considered a passive circuit. That is, total flow is not regulated. The systemic and pulmonary circuits are connected in series, and you cannot independently regulate two structures connected in series. Therefore, we regulate the flows through the systemic structures, and because of that, we cannot regulate the total flow through the pulmonary circuit. So the pulmonary circuit just receives whatever we deliver to it. You cannot regulate the total flow through this circuit. It is incorrect to think that sympathetic neurons run to arterioles in the pulmonary circuit to change resistance in order to regulate flow. It is a passive, non-regulated circuit in terms of total flow. Now, another important characteristic is that the entire pulmonary circuit is a very compliant circuit. Both the arteries and the veins are very compliant vessels. If you've ever looked at a pulmonary artery or had the opportunity to touch a pulmonary artery, it almost appears similar to a systemic vein. It's because its structure is very similar. Both of those are very compliant vessels. So the entire pulmonary circuit is a very compliant system. Another characteristic that we will reemphasize in respiration is that the pulmonary circuit demonstrates a phenomenon called hypoxic vasoconstriction. Now, this phenomenon is restricted to the pulmonary circuit. We'll reemphasize it later, but hypoxic vasoconstriction is initiated whenever you have a low alveolar PO2. And a low alveolar PO2, in some way, shape, or form, will cause a local vasoconstriction. And this is one mechanism where you can control the distribution of flow in the pulmonary circuit. So you can regulate the distribution of flow through the pulmonary circuit, but you cannot regulate the total flow through this circuit. Now, another characteristic, which may not be obvious, is that blood volume is proportional to blood flow. Every once in a while, they may test the point that the volume stored in the pulmonary circuit is proportional to cardiac output. So if you increase cardiac output, more blood is stored in the pulmonary circuit. If you decrease cardiac output, less blood will be stored in the pulmonary circuit. So the amount of blood stored in the pulmonary circuit is proportional to cardiac output. Now, another point, again, based upon the passive compliant nature of this circuit, is that pressures in the pulmonary circuit are proportional to cardiac output. If you increase cardiac output, you will always increase pulmonary pressures. If you decrease cardiac output, overall pulmonary pressures will decrease. Again, it's because it's a passive, non-regulated circuit. Now, finally here, large changes in cardiac output will produce only small changes in pressure. This is because it's a very compliant circuit. If you increase cardiac output, you will always get a passive vasodilation, and that will minimize the increase in pressures. If you decrease cardiac output, you will always get a passive vasoconstriction, and that will minimize the drop in pressure. So the passive compliant nature of this circuit minimizes the changes in pressure when you have dramatic changes in cardiac output. Now, the standard situation they like to test on step 1 to see if you understand the pulmonary circuit is the pulmonary response to exercise. Now, the assumption here is you're performing fairly moderate exercise or even heavy exercise. Therefore, under these conditions, there is going to be a large increase in cardiac output. Now, if you increase cardiac output, pulmonary pressures will increase. However, as pulmonary pressures increase, you open up more vessels, you passively dilate vessels, and this causes a large decrease in resistance. Therefore, then, during exercise, a large increase in cardiac output will cause only a small increase in pressure because there's a very large decrease in resistance. And they do expect that level of quantitation in the question. Now, the opposite situation, which is described in your notes, is the pulmonary response to hemorrhage. Now, this is almost exactly the opposite of exercise. Just read through this on your own. It is not tested as often, but it's simply the opposite situation to exercise. Now finally here, we have a figure that details the characteristics of the fetal circulation. Now what you should understand here are basically the unique characteristics of the fetal circulation. And there's just 4 or 5 points that are important here. First of all, the blood that is moving through the descending aorta is only about 60% saturated. The hemoglobin is only about 60% saturated with oxygen. And this modestly oxygenated blood, some of which will go to the umbilical system. And you should realize about 50% of the cardiac output in the fetal heart will go to the umbilical circulation. Now the venous blood coming from the placenta will have picked up oxygen, and the saturation of the hemoglobin here is almost 80%. Now this is not completely saturated blood. It's about 80%, but it's fairly close to saturation. Now this blood coming through the placental vein then will eventually mix with blood in the inferior vena cava. And this will decrease the oxygen saturation a little bit. This decreased saturated blood then enters the right atrium. It passes through the foramen ovale and then is pumped by the aorta, and most of this blood will go to the head and neck region. And this blood is about 65% saturated with oxygen. On the other hand, the blood coming from the superior vena cava, which is 40% saturated then, enters the right side of the heart and is pumped by the pulmonary artery, and this blood will pass through the ductus arteriosus and pass down the descending aorta, and much of this blood will go back to the umbilical circulation. So those are the unique aspects of the fetal circulation that you should remember. Now this finishes off the peripheral circulation. There is one additional topic here, that is AV differences. This is considered a supplemental topic. It is not totally unimportant. There are questions in this area, but after the theory here, we have some questions in the handout with answers and explanations at the end of the section. So spend some time answering these questions just to see if you understand AV differences. Now the next section in the physiology handout, section 4, is the physiology of skeletal muscle. Now I want to point out here, the boards does not intensively test skeletal muscle physiology. However, certain aspects are routinely tested, that is, those aspects that can be applied to cardiac muscle. Therefore, we consider skeletal muscle more a prerequisite to heart muscle physiology. That is where most of the questions will come, but they will test common points in these two muscle systems. Now, we're going to start off by going through the main points at excitation, contraction, coupling. And most of these points will apply to both skeletal and cardiac muscle. But before we get into the major aspects here, I just want to review a few points about the ultrastructure of a skeletal muscle fiber. More specifically, I want to go into a few aspects about the organization of a sarcomere. Now, I assume that everybody knows the general organization of the sarcomere and has a good understanding of the sliding filament theory for muscle contraction. Now, all I want to emphasize here is that the various bands or zones in a sarcomere may or may not change their length during contraction. And every once in a while, they will ask you which do shorten and which do not shorten. Now, if we start by looking at the A band of a sarcomere. Now, the A band of a sarcomere represents the entire length of a thick filament. And because the entire length of a thick filament does not change with muscle contraction, the length of the A band will never change with muscle contraction. Now, if we go to the I band of a sarcomere, now the I band represents that part of the thin filament in which there is no overlap with the thick filament. So the I band represents only part of the thin filament. It is that part in which there is no overlap with the thick filament. Now, because of the thick and thin filaments sliding past one another, the I band will shorten during muscle contraction. So because of the sliding past one another of the thick and thin filaments, the I band will get shorter during muscle contraction. Now, the last region of the sarcomere to deal with here is the H zone, sometimes called the H band. The H zone and the H band are really representing the same region. Now, the H band represents that part of the thick filament in which there is no overlap with the thin filament. And therefore, again, because of the sliding past one another of the thick and thin filaments, the H zone or H band will also shorten during muscle contraction. So in summary then, during muscle contraction, the A band does not change length, but the I band and the H band will shorten during muscle contraction. Now, that's all I really want to mention about the organization of the sarcomere. Then nothing else beyond the general organization is important. Now, I also want to say a few things about the ultrastructure organization of the sarcoplasmic reticulum, but in general, I just want to say a couple of things about the overall membrane system in skeletal muscle. First of all, you should realize the T-tubular membrane system, shown right here, is simply an extension of the surface membrane. It is important to remember that the T-tubular membrane system is simply an extension of the surface membrane. That means that the interior of a T-tubule system then, the interior of a T-tubular system is actually part of the extracellular environment then. So the interior of a T-tubular system is part of the extracellular environment. Now, the other aspect here relates to the title, that is the sarcoplasmic reticulum. And there's two big points here. The sarcoplasmic reticulum is an internal membrane system that stores calcium. And the second point is that most of this calcium is stored in the terminal cisternae of the sarcoplasmic reticulum. Now, these terminal cisternae approximate the T-tubular system. And what I want to emphasize is that most of the calcium stored in the sarcoplasmic reticulum is stored very close to the T-tubular system. Now, those are the only points I want to emphasize about the membrane system in skeletal muscle, and that material will also apply to cardiac muscle. What I want to address next is the general organization of the thin and the thick filaments. Now, if we begin with the thin filaments, you should realize that thin filaments are made up of 3 different proteins. And you have to know the role played by each one of these proteins. Now, if we start with actin, the big point about actin is that actin is basically the structural protein of the thin filament. So actin is the structural protein of the thin filament. If you look at a figure representing a thin filament, they usually show it as globs of actin all connected together to form a thin filament. Now, there are 2 chains of actin, but all you have to remember is that actin is the structural protein of the thin filament. Now, the other point about actin that is important here is that actin has the attachment sites for the cross bridges. So each actin molecule here will have an attachment site for a cross bridge. Now, they may not test it this way on step 1, but the other two proteins here are not structural proteins. Tropomyosin and troponin are regulatory proteins. And you need to know the role played by each one of these proteins. Now, tropomyosin's job as a regulatory protein is to physically cover up the attachment sites on the actin in a resting muscle. So because this represents a resting muscle, this tropomyosin molecule here physically covers up the attachment sites on the actin. And because it physically covers up the attachment sites, these attachment sites on the actin are not available to the cross bridge under resting conditions. Now, the other regulatory protein is troponin. Now, troponin is actually attached to the tropomyosin. The troponin is physically attached to tropomyosin. Now, the job of troponin is to bind calcium. So each troponin molecule must have a site that has very high affinity for calcium. Now, the next few points are very important in understanding overall muscle contraction. Under resting conditions, the troponin has no calcium attached to it. So under resting conditions, when there is no calcium attached to the troponin, the tropomyosin physically covers up these attachment sites on the actin and makes them unavailable to the cross bridges. One of the earliest events in contraction is the release of calcium from the sarcoplasmic reticulum. And once the calcium is released from the sarcoplasmic reticulum, it is considered to be free calcium in the cytoplasm. And once it is free calcium, this calcium will diffuse towards the troponin. Now, once the calcium attaches to the troponin, that attachment of the calcium to the troponin causes the tropomyosin to physically move. And when it physically moves, it exposes the attachment sites on the actin. And you should realize for sure that as long as the calcium is attached to the troponin, these sites on the actin are available for the cross bridge. And they are available throughout the process of contraction. As long as you are in the contraction mode then, the calcium remains attached to the troponin and the cross-bridge attachment sites are available. When you terminate contraction, you remove the calcium from the troponin, and when that occurs, the tropomyosin quickly moves up and covers up the attachment sites on the actin. Now, just to summarize the main points here, because they're very important bottom line points here. Under resting conditions, there is no calcium attached to the troponin. And when that exists, then, the tropomyosin covers up the attachment sites and they're unavailable to the cross bridge. When you initiate contraction, the free calcium in the cytoplasm attaches to the troponin. The calcium attaches to the troponin, the tropomyosin moves, exposes the attachment sites. And as long as you're in the contraction mode, the calcium remains attached to the troponin. When you terminate contraction, you remove the calcium from the troponin, the tropomyosin moves back in, and the attachment sites are no longer available. Now, that is very important information to remember. It applies both to skeletal and cardiac muscle. Now, going to the thick filaments, there's just a few points I want to mention here. The main protein and the structural protein of the thick filament is myosin. More importantly, the thick filament contains the cross bridges. You should realize the cross bridges are an integral part of the structure of the thick filament. But the most important point is these cross bridges on the thick filament will have ATPase activity. So looking at the figure here, this represents a cross bridge head here, and you have to realize that this cross bridge head does have ATPase activity. Now this ATPase does not break down ATP in a resting muscle. Under resting conditions, the cross bridge has ATPase activity, but it is not breaking down any ATP. This enzyme only breaks down ATP during the process of contraction. And the most important point is the ATP broken down on the cross bridge during contraction supplies the energy for the mechanical aspects of contraction. And this can be in the form of either the development of active tension or active shortening. Now, active means the energy is derived from the breakdown of ATP. And it is very important to remember that the energy to provide the mechanical aspects of contraction is derived from the breakdown of ATP right on the cross bridges. Now that finishes off the details of what I want to mention about the organization of the thick and thin filaments. The next topic here is to go through cross-bridge cycling. Now cross-bridge cycling is not fully understood. So boards or step 1 may not test a lot of the details here, but they will test the basic fundamental points that most people agree on, and that's what we will emphasize. Now we will start off with this figure here that represents the situation in a resting muscle. Under resting conditions, the cross bridge sticking up from the thick filament will be simply sitting in midair. It will not be attached to the actin. But this cross bridge will have both high energy and high affinity. Now they may not test it on step 1, but the last event was the hydrolysis of an ATP right on the cross bridge. And the breakdown of this ATP, the energy released, will be stored in the cross bridge. So under resting conditions, this cross bridge is considered a high energy cross bridge because an ATP was broken down in the last contraction, and that energy is stored in the cross bridge. But more importantly for step 1, you have to know that this is a high affinity cross bridge. This cross bridge has extremely high affinity for the actin. The only reason this cross bridge does not attach to the actin is the tropomyosin is in the way, and it prevents cross-linking to the actin. So the most important point here is, under resting conditions, this cross bridge has high affinity for the actin. The only reason it does not attach to the actin is the tropomyosin is in the way. Now, to start the cycling, we're basically starting contraction. So by definition, starting cycling means you start the processes of contraction. And you start cycling by simply having available some free calcium. So free calcium will start the cycling because this free calcium will attach to the troponin, the tropomyosin moves, it uncovers the attachment site on the actin, and the cross bridge will simply link with the actin. The big point here is all you need to start cycling, all you need to start contraction is free calcium. You don't need any ATP to start the cycling because the cross bridge already has high affinity for that site on the actin. Now that point is important for step 1. The next point possibly is not tested on step 1 because the details are not well understood and people teach slightly different things here. But basically, this is a high energy cross bridge. Once the cross bridge attaches to the actin, because it is a high energy cross bridge, the cross bridge will hinge. And when the cross bridge hinges, you have basically converted the chemical energy stored in the cross bridge into the mechanical aspects of contraction. This is where you have sliding past one another of the thin and thick filaments. So when this chemical energy stored in the cross bridge then is converted into the mechanical aspects of contraction by hinging, you get sliding past one another of the thick and thin filaments. Now, as I said, that is probably not an important point for step 1. But the next one is a very important point for step 1. Once this cross bridge has hinged, you expose a site on the cross bridge that has high affinity for ATP. You specifically expose a site. It has a site for very high affinity for ATP. Now the big point here is once the site is exposed, then you will have binding of the ATP to the cross bridge. And the actual binding of the ATP to the cross bridge causes the cross bridge to lose affinity for the actin. And once it loses affinity, it lets go of that site on the actin. One of the most important points here is it is the attachment of the ATP which causes the cross bridge to lose affinity and dissociate itself from the thin filament. Now the bottom line statement that relates that is the following, and this is important for step 1. ATP is not required to form the cross-link between the actin and myosin. ATP is required to break the cross-link between the actin and myosin. So you don't need ATP to form that cross-link. You need ATP to break the cross-link, and that's one of the most important points in cycling. Now, just to add a detail, which again may not be tested on step 1, once the cross bridge lets go of the actin, then it still has the ATP attached to it. But once it lets go, then the ATPase on the cross bridge will now break down the ATP, and when it hydrolyzes the ATP, that cross bridge not only gains energy, it will gain affinity for the actin. So you're back at position 1, right where we started. Now, if you're still in the contraction mode, you don't stop at position 1. You continue to cycle. And a bottom line point is contraction by definition is the continuous cycling of cross bridges. Now, students are always asking for a definition of contraction. And by definition, contraction is the continuous cycling of cross bridges. If the cross bridges continue to cycle, you are still in the contraction mode. That also means if you terminate contraction, you're basically terminating cycling. So relaxation simply involves terminating the process of cycling. Now there's two ways in which you can terminate cycling. The first way is the natural way. And the natural way is to actively pump the calcium back in to its storage depot inside the sarcoplasmic reticulum. And if you remove the calcium, you should understand that you would stop at position 1, where the cross bridge is not attached to the actin, because ATP is not required to form the bond. ATP is required to break the bond. Now, the only other way to stop cycling, and it's not a natural way, is for the cell to run out of ATP. Now, if you run out of ATP, then you should understand that you terminate cycling at position 3. And again, the bottom line point is, if you run out of ATP, you would end up with a cross bridge attached to the actin, because ATP, again, is not required to form the bond. ATP is required to break the bond. Now, if you stop at position 3, this would be equivalent to the state of rigor mortis. Now, rigor mortis is not an active event. Rigor mortis is simply a passive event. All you need for rigor mortis is some free calcium in the absence of ATP. The free calcium will cause the cross-link between the actin and myosin, and if you don't have ATP, you simply stop at position 3. Now, those are the important points regarding cycling. Now, what we're going to do next is we're going to put it all together. We'll put contraction relaxation steps into a flow series of events here, and none of these points are minor points for step 1. All of them are very important points that they have tested in the past. Now, again, I want to emphasize what we're specifically referring to here is skeletal muscle. But most of these events will also apply to cardiac muscle. But more specifically, we are referring to skeletal muscle. Now, we're starting at the point where the action potential is generated at the neuromuscular junction. And once you generate the action potential, this action potential not only spreads across the surface of the skeletal muscle membrane, you also have to know the action potential will spread down the T-tubules, but this is where it terminates. The action potential will terminate at the level of the T-tubular system. The action potential does not spread across the sarcoplasmic reticulum. The sarcoplasmic reticulum is an internal membrane system, and internal membrane systems cannot have action potentials. Now, it is not fully understood, but the action potential going down the T-tubule, which is illustrated right here, the action potential going down the T-tubular membrane will cause foot processes to be removed from the calcium release channels then. And most of this calcium is stored close to these channels in the terminal cisternae of the sarcoplasmic reticulum. Now, once you remove those foot processes then, the calcium stored in the sarcoplasmic reticulum will be released into the general intracellular environment, and once it is